Alrighty, let's try again. So, okay, we have 6 more lectures. One of them, well, 7, but one of them will be a challenge level, and that's going to be now on April 21, which is 2 weeks from today. It's your final challenge level. Lots of stuff about, is that good? Is that bad? Oh, see? Very thoughtful. All right. You'll have a lovely day. Okay, so that's going to be eigenvalues and eigenvectors and all those good things, a few other pieces like Graham-Schmidt and so on. But the remainder of the course, we're going to come across all sorts of goodies, right? We've piled up all of these skills and abilities, and now we're going to unlock all sorts of things about matrices. I know you're thrilled about it. Lots to do with eigenthings, right? So this is fundamental equation, AV equals lambda V. We're going to dig into this over the next 4 lectures. And I'll try not to collapse. Okay. Seriously, pulmonary, not good. Okay, so we've got this. Today I'm going to give you a selection of sort of a summary of kind of quirky, interesting, useful little results for eigenthings. There's some very surprising things that start to come piling out of these matrices. Again, this is for n by n matrices, square matrices. And then today, hopefully, once I collapse, we're going to have this rather remarkable factorization of a square matrix. It's not always possible. It's possible many times, but many cases. But it's going to be this funny-looking beast. And that's a capital lambda in the middle, big lambda, right? Here's a baby lambda. They're very cute. That's a baby lambda. That's a big lambda. And these s's, I'll tell you what they are, but it's s and s minus 1. There's some nice symmetry there, and that's what's going to happen. This is a diagonal matrix. This is what this matrix A really is. If you look at it the right way, it's really a diagonal matrix. And diagonal matrices are very, very simple. So that's the story here. Diagonal matrices are very simple. Many matrices really are diagonal matrices if you look at them the right way. All right. Okay, I've said these things. Let's see. Up on the slides we have your next level. Here it is pitfall. It's number 8. There's going to be 2 more with some increasingly silly themes related to computer games. All right, so pitfall. So that's a lot of, what's it got in there? Lots of, right, there's some determinant stuff. Eigenvalues come in here again, eigenvectors, but lots to do with determinants, actually. All right, okay. So, while I was away, I eventually did add 3 lectures that, if you have not looked at them, I want you to. There are 3 components of a lecture, if you like. So, let's see. So, they're all about determinants. One is properties of determinants. We'll do sort of a similar thing today with eigenvalues. So, there's a big grab bag. You've got to know all these things. The cofactor method. That's what we really kind of need for 3x3s to figure out determinants when we're solving the eigenvalue problem. And then Cramer's rule and a formula for the inverse of a matrix, which is kind of strange, but there really is a formula for it. And so that's all in here. They're not too long. I guess this one's 40 minutes. This one's like 25. This one's 20. Absorb those, please. Okay, so I can get rid of that, I think. And I am done. Okay, yeah. Let's see. Okay, let's do things on the board. Oh my God, people. All right, okay. Flying spaghetti monster. Any questions? We doing all right? Okay? Okay, so, all right, team. Someone is paying money. I don't know who's paying money. Let's be quiet. All right. Okay, I'm sorry. Hey, let's go back. So, all right, so back to eigenvalues and eigenvectors, and let's find out some things about these. So these are really a beautiful part of linear algebra and science. Okay, eigenvectors. Okay, so the game is this. AV equals lambda V. And I gave you reasons for why this thing matters. This equation appears in many, many places. This is an n by n. This is an n by 1. It's the same vector here. So in general, what we have is, and I'll go over some of the things that you've just finished in this assignment, just to put them in a big list. And this is just a scalar, right? So this is a number. So these are the directions that A likes. A, if you multiply this vector by A and you think of A as a gadget, it's doing something to it, it's like trying to rotate it or stretch it or do something, it'll give you that vector back, just multiply by a number. All right. So we're going to have sneaky tricks, sneaky observations first, and then the factorization business. All right. So sneaky tricks. Let's call them sneaky tricks. All right. All right. So, let me just write down exactly what we're doing again. So we've got this equation. So again, it's going to be a struggle today. We're doing one. We're going to solve this. A minus lambda I. The determinant of this has to equal 0. So that's the big observation, right? So because we start with, I know it's been a while, so let's do it again. A equals lambda v. We've got this. We figured out last time that I was alive that you could do this. You could insert an identity matrix in here. It's still the same. This equals 0. And then we could factor these parts out times v. And we used all of the stuff that we started with, right? The big picture story. There is a v, right? There's a non-zero v only if this thing has a non-trivial null space. A minus lambda I has a non-trivial null space. It's another way of saying it. And what's that equivalent to? Well, that's equivalent to a lot of things, which is in one of those videos there. It's equivalent to many things. So this is, again, it's a square matrix. So I'm going to say that this doesn't have a null space. I mean, has a non-trivial null space. It's the same as saying that it has no inverse, does not exist. And then this big observation, this whole detour and determinant world, was that we showed that this is also the same as saying the determinant of whatever matrix we're talking about equals 0. Right, so with determinants, I want you to think about the rows or the columns as vectors that constitute the basic structure of a parallelepiped, which hurts so much to say that we don't even draw them. We draw parallelograms, which is enough. Right. So the volume is 0, right? So that there's linear. Another way to say this is that the rows of A minus lambda I are linearly dependent. Dependent, not independent. All of those things, lots of things connect together. Okay, there are many ways to sort of get at this, but we sort of decided long ago, lots of monks have decided that the best way to attack this is to say, let's find when the determinant is equal to 0. Let's compute a determinant and find the values of lambda for which that determinant is 0. So once we've got the lambdas, right, so 1 gives lambdas, and then 2, we substitute lambdas into a v, this problem, I guess, a minus lambda I times v equals 0, and find the v's. Right, we'll do an example, well, we'll talk about an example a little bit. And these are the eigenvectors, okay? So E values, E vectors. Now there's a problem in your assignment, the one you just did, or one that's coming, I'm confused, which talks about the problem. So sometimes, if you have a repeated eigenvalue, you don't always have enough eigenvectors. You don't always get enough eigenvectors out of it. So there's a little video about that. And the words we use are geometric multiplicity and algebraic multiplicity. I'll mention them again. But generally speaking, we always have n eigenvalues, we don't always have enough eigenvectors. So they're bad matrices. We're sad. They're really not, they're not good matrices. Okay, they're not good. All right, okay. And that's not what we want for this glorious thing over here. Okay, so this is our game. So sneaky tricks. Okay, so let's find out some things about this. So sneaky trick 1 is that this is true. This is kind of odd. So A equals product I equals 1 to n of lambda I. You multiply the eigenvalues together, you get the determinant of A. That's a bit strange. So let's do a small example that we'll carry through. And we've looked at this one before. Probably treat it slightly differently. A equals 1, a half, 1. There's something important about this matrix. It's 2 by 2, so it's very small, but it has a property symmetric. So A equals A transpose. Big deal later. It's a huge deal. Crazy. Okay, that's just a little side note. We'll come back to it. Just put a little flag there. Okay, that's going to be our example. We've worked with this one before, and you find that lambda 1 equals 3 halves, v1 equals, and I'll say 1, 1. And lambda 2 equals a half. So we find these things. V2 equals, and I'm going to make it minus 1, 1. Now, we could choose any multiple. We could choose any multiple. So it's just a note. We could choose any multiple. 1 minus, these are simple ones. So that's good. It's sort of silly to choose 7, 7. A nice one would be to divide it by root 2, make it length 1. So that's the only kind of other sort of sensible one. Could choose any multiple. Eigenvalues, that's it. Eigenvalues are 3 halves and a half. You don't get to mess around with them. They are part of this matrix. Eigendirections are fixed, and the eigenvectors, people sort of talk about eigenvectors as if there's only one of them, which is a bit odd, but the eigenvectors are bases for those, what are really the null spaces of these things. All right. So here's our little example. Let's just look at a couple of pieces here. What's the determinant of this thing? Yeah, what's going on?
I was wondering if you could clarify that I looking at this time.
Oh, right. Okay, yeah, right. Yeah. Okay. Yeah, so the big S will have, the sigma will have in a second. We'll get to that one. You like that one, right? Yeah. So that's sum, S for sum. Yep. So this is P for pi. So it's pi for P, as in Greek, right? So it is P, and it's product. So take the eigenvalues and multiply them all together. Okay. So good question. All right. Yeah, so the product of the eigenvalues is equal to the determinant. The determinant for a 2 by 2, we've worked it out either online or, I guess I did do that, a parallelogram. Right, okay. Of A equals, and in general, the determinant of A, B, C, D equals AD minus BC. All right, so let's use that. So we have 1 times 1 minus a half times a half, 1 times 1. We're just testing this. It's just a test. Just a check for one thing. It proves nothing. So it's 3/4. Oh my God. Basic algebra is going to kill me. All right, so determinant of A is that. Product of the eigenvalues. Lambda 1 times lambda 2 equals 3 halves times a half equals 3/4. Strange little business. So why is that? So why? So let's just keep focusing on a little 2 by 2, and then we'll make it a n by n problem. So why? Okay, so let's see. We're going to do give us an opportunity to do this. This is how we would find our eigenvalues in the first place. So let's look at this equation. And what is it? So it's the determinant of 1 minus lambda, a half, 1 minus lambda, right? And that equals, so this is the left-hand side, if you like, of what we just had there. So this is 1 minus lambda all squared minus a quarter. And, well, if we expand this out and collapse it, then we'll get lambda minus, no, we'll get this, a half, 3 halves minus lambda, a half minus lambda. Right, if we go through it. So this is the point is that the roots are, right, the roots, right, set equal to 0. Roots equal 3 halves and a half. Right, that's how we find our eigenvalues. So this is this determinant in general. If we observe this. So before we go any further with this, so we observe that if we set lambda equal to 0 in a minus lambda I, right? So we are getting lambda 1 and lambda 2, they're going to be these numbers, but this is actually just a tunable number. It's a tunable beast, right? We can just set lambda anything we want. Well, we can do that, right? We can dial it from minus infinity to infinity. And that's essentially what we're doing. We're saying, well, these are the only ones that are really interesting. What if we set lambda equal to 0 here? What is this now? So we set this in just the determinant of A, right? So we set this, we get determinant of A, right? So this goes away. So if we go back to our equation here, so back to, I can't prove all of these things completely. I'll have to, some of them I have to kind of show a little bit. 3 halves minus lambda, a half minus lambda. So we set lambda equal to 0 here. And really what this is, of course, is this is lambda 1 and this is lambda 2. So A, the determinant of A, will equal lambda 1 times lambda 2. So you're treating it as a quadratic as a function of lambda here and just setting lambda equal to 0. Right? More generally, this is lambda 1 and this is lambda 2. And so generally, for an m by n, we get this. When we solve this thing, we'll get lambda 1 minus lambda, lambda 2 minus lambda, out to lambda n minus lambda. Right? And we're not setting it equal to 0. And again, set lambda equal to 0. And then we'll get, on this side, we get just the determinant of A. And on this side, we get lambda 1. This has gone away. This has gone away. All these ones out here equals lambda 1 times lambda 2 times lambda n, which is the product of I equals 1 to n of lambda I. So it's a bit sneaky, but it's always true. So it's always a little test you can make if you're computing eigenvalues and you have your determinant laying around. You can just check, right? All right, that's one thing. Just connecting, so the eigenvalues have this connection to the determinant. It's a very profound connection. So this is sort of structural pieces we're building up. I'm going to call this next one, sneaky trick 2. So we wanted a sum, so we'll have a sum. Let's do a sum. Does anyone know what this thing is? Anyone seen that thing? It's T with a little r. This is the trace of A. And that equals the sum. This is an odd thing, the sum of the elements of A on its main diagonal. Believe it or not, this really is a big deal. Sum of elements of A on A's main diagonal. Whoa. Okay, so that would be, in our matrix notation, A sub I equals 1 to n, right? So it's this. That seems like a funny thing to do, but that is the trace of A. Traces have beautiful properties, and here's the result. So this is a definition. Trace of A equals the sum of the eigenvalues. This thing? What's this thing? Oh yeah, this bit. So I equals 1 to n. Yeah? Is that okay? Did I get it right? Chalk. And so here's the thing that I'm really excited about, and so are you, of course. So the trace, that's weird because these things are buried inside. The determinant is something that's buried inside as well. That's a strange object. This is just sitting in A, right? Sitting in A. Just the numbers just sitting there. These are buried. Right? It's hard to get eigenvalues out. You got an n by n, you're trying to get all the eigenvalues out. Often we just say, oh, let's get the biggest one. We can't. It's too hard. Okay. How are we doing with that? So let's look at it. We'll look at our example, and I'll give you a rough kind of story for what happens in general. I'll mindlessly take photos of things. Oh my God. Okay. Okay, so what's going on? Our example, what is going on? Let's have a look. We have the trace of A. It's 1, 1, a half, a half. So the trace of that is, we're just going to add this one to this one. Equals 1 plus 1 equals 2. Strange connection. All right. That's true. And then the sum of the eigenvalues is 3 halves plus a half equals 2. So that's good. One example, just one example. Okay, so let's do a general example. So let's do a general example, general 2 by 2 example, just to kind of figure this out. So let's say we have A equals ABCD, BCD, and we're going to compute the eigenvalues for this thing. Right, so we set this up, set it equal to, all of this has to be equal to 0. So it's going to be the determinant of A minus lambda, B, C, D minus lambda. That's good. Let's get this properly. So it's A minus lambda times D minus lambda minus B times C. And then I want to expand that one more piece. So let's get the lambda squareds here. So there's a lambda squared. You know what I'm going to do too? I'm going to put minus lambda all squared. I'm just going to keep it as minus lambda because there's this sort of structure of minus lambda here. Okay. And then it is plus A plus D times minus lambda. And then there's a AD minus BC plus AD minus BC. That's a bit cramped, isn't it? All right, let me put it up here. Let me put it up here. Okay, so this is going to be, for a 2 by 2, this is the general form of the A minus lambda I calculation, the determinant, so minus lambda squared plus A plus D times minus lambda plus AD minus BC. So here is the, what is this thing? Yeah, it's sitting right there. So trace of A, what's this? Yeah, it's the determinants there. So, in fact, right, you have lambda to the n by n, and you compute everything out. The bit that's sitting on the end, the constant term, will be the determinant of A. This is always a constant piece is always the determinant of A for n by n's. And you can see why again, because lambda equals 0, it crushes this part, all of that goes away, and we have to have the determinant of A equals the determinant of A. So let me say one other, I haven't said this word, this yet. This thing is called the, it kind of came a little late here, the characteristic, sort of a name. We have a name for this equation, it's so important. Right, this equals 0, it's the characteristic equation. Equation of A. It's just a really fundamental thing. Characteristic equation of A. That's a little side bit. When it equals 0, it's the equation. Yep. Yep. Good. A little puzzle for you is to think about this is that the matrix A satisfies its own characteristic equation. If you replace lambda by the matrix A, compute it all. Okay. Let's leave that just where it is for now. Okay, let's, so this is one way to do this, but at the same time, but we also know, we also have to have, right, we're solving this thing, we have to have A minus lambda I. All right, what's going on? Lambda I equals lambda 1 minus lambda, lambda 2 minus lambda. I'm just going to erase that because it's not there anymore. And if we expanded this, then we get minus lambda squared, we get plus lambda 1 plus lambda 2 times minus lambda, and then plus lambda 1 lambda 2. So look, this is taking the general form of a 2 by 2 and computing it all out, and then noticing a few things. Noticing the trace of A appears attached to the minus lambda term. That the determinant of A appears here as a constant term. But also generally, we're going to have to end up with this equation. It's going to be this quadratic, and it'll be lambda 1 minus lambda, lambda 2 minus lambda. They're the roots of this equation, right? And for this example, it's 3 halves and a half. Expanding that, we get our minus lambda squared, so that matches. We get A plus D and lambda 1 plus lambda 2, so this is the sum of the eigenvalues. Right, so the sum of the eigenvalues is equal to the trace of A, and this is the product of the eigenvalues, and that's equal to the determinant of A. So just for so this is a general 2 by 2 example, we have the result. I'll just show you, I'll give you a sense of what happens for n by n's. Right, so the trace of A equals the sum of the eigenvalues for 2 by 2. General 2 by 2. And then an n by n, when you do these same things, what's going to happen is, here's my little piece of paper, you'll get, which one did I put at the top? That one. Okay. You're going to end up with minus lambda to the n plus the trace of A times minus lambda to the n plus 1, n minus 1, sorry. And then and then you get down to the determinant of A will be the constant term. And you'll also have, at the same time, the sum of the lambda i's will appear in that term. This is it takes a little more to think about this. So we get this match here. So in expanding the characteristic equation, the one side of it, the piece that's attached to the minus lambda to the power of n minus 1 will be the trace. There's always a 1 in front of this one. And if we, right, this whole thing is coming from lambda 1 minus lambda, lambda 2 minus lambda, lambda n minus lambda equals 0. This is what has to happen when we do our a minus lambda determinant, lambda I determinant. Okay, that's generalizing. Right. All right, so these two things are true, right? So the product of the eigenvalues is equal to the determinant of A. It's always true. There's no sort of ifs or buts there. And the sum of them is equal to the trace of A, which is a strange thing. Okay, so what's a... I'll just call them sneaky tricks. So sneaky trick 1 tells us something straight away, that the product, the determinant of A equals the product of these guys implies some, so there's sort of one interesting value of the determinant of A, which is that we kind of look for, or we worry about in general for a matrix. There's one critical value of its determinant, which, you know, upsets apple carts and things. 0, right? So we're worried about when it's 0. So the determinant of A equals 0 corresponds to, what can we say about its eigenvalues? Must be one or more of them has to be 0, right? Good. One or more of A's eigenvalues equals 0. That's exciting. I know it's exciting. So as soon as you see a 0 eigenvalue, it's like, okay, that this matrix has a 0 determinant, and therefore it has a null space that's not 0, and you know it's a little deficient in some ways. Okay, so that's one thing. All right, for those of you who looked at the determinant stuff, there was a connection we made between determinants and pivots. What is that? From online lectures on determinants. Anything to do with the pivots? Anything? All right, you're going to have to look through this. This is the pivots we call DI, right? Plus or minus. So it's a product of the pivots as well. So the determinant of A is this. And then we have this connection between these two very different parts of linear algebra. And this is sneaky trick 1. So product of the pivots is equal to the product of the eigenvalues up to a sign. And so this sign comes from, actually comes from this, PA equals LU. If you go through this, it's the sign plus means even number of row swaps, and minus means an odd number of row swaps. Right. So you do row reduction. We're allowed to do row reduction when there's a whole business there. You got to look at that with determinants. It's quite magnificent. And everything we did with our very formalized way of doing row reduction from the start, our rules, they come back to help us, not haunt us. They come back to help us again when we work with determinants. So this is an odd connection. There aren't many other. There's actually a more subtle connection, but this is a strange thing. Multiply them all together, all the eigenvalues, and multiply all the pivots together, and up to a sign they're the same. It's strange. Okay. So that should be number 4. All right. This is a strange connection. And they're very different things. A equals lambda AV equals lambda V, that's what we're solving here for eigenvalues, right? It's just a different game altogether to finding pivots, which is what we do when we go through triangularization. Okay. Okay, so you guys have, and that's the connection. They're not the same things at all. Okay, I'm going to list these because you already have them from your 5 in your problem set. So if this is true, AV equals lambda V, that's the basis, right? Then A to the power of n times V, right? We can replace each one of these, so let's do it. A n minus 1 times AV. We can use this relationship straight here, right? So each one of these can get turned into a lambda, and so we'll end up with lambda n to the V, lambda to the n times V. Okay? So V is an vector of A with E value lambda to the n. Right, just a simple little argument. Okay, that's good. Now let's do another one. So you did a few of these. Yeah, so if we have, and this one certainly happens. So again, if this is true, AV equals lambda V, then we can do this. If we shift, that's a K, we add kind of a shift to the main diagonal, right? So this is really saying add K to A's main diagonal everywhere. Identity is a very natural thing to mess around with, right? So this times V equals A times V plus KI times V. This is, we've already got this. I times V is V. And then we can extract these two, lambda plus K times V. Right, so again, same kind of argument. V is an E vector of this new matrix A plus lambda K, A plus K I with E value lambda plus K. Right, easy little things to prove. The short proofs. Okay. And can I squeeze another one in there? Maybe. Okay. Last one in here in this little section. Right. So again, if AV equals lambda V, that's our start, right? That's true. That's true. Then we can move A to the other side. We can mess around with it like this. I'm going to multiply both sides by A to the minus 1 equals A to the minus 1 times lambda V. This lambda, we can extrude it through there. This is just the identity matrix. So now we have V equals lambda times the inverse of A times V. And I'm just going to put that's a lambda. I'm going to put this guy on the left-hand side, A to the minus 1. A to the minus 1 times V equals 1 over lambda times V. So if you want any kind of eigenvalue equation, right, it has to be matrix times a vector equals some number times a vector. And we've messed this around so that now it is the inverse of A times a vector, 1 over lambda. And that actually fits with this formula back here too. So if we put n equals minus 1, you get lambda to the minus 1. Exciting. Okay. All right. You had those things. Okay, so now we start to get to some slightly curious bits. How we doing? All right. I think we're going to do diagonalization. Good. Good, good. Okay, this looks like it's true. Okay, this is another one where we prove it just a little bit for a simple case. So, think about this. Wow, sneaky trick 8. Still here. Huh. Palimpsest. Okay. Okay, so here's a tricky thing. So if A's eigenvalues are all distinct, that means no repeats, right? We don't have lambda equals 4, 4, 4, none of those, no repeats. Right? Then the eigenvectors of A, right? Each one has an eigenvector. Each eigenvalue will have an eigenvector, form a basis for Rn, let's say that. Right? They're linearly independent. So this is a big deal. So that means that matrix, it means that the matrix has enough, the vectors it likes are enough to actually describe the whole space. We can move away from I hat, K hat, J hat, whatever it is, I, J hat, I hat, J hat, K hat. We can move away from those into the eigen directions of this matrix and everything will be better. All right, let's get to that. So let's see. So here's just a sort of a reason for 2 by 2s. A reason for 2 vectors. Lots of sneaky little calculations involved here. So let's imagine we have, we've got 2 of them, right? V1 and V2. So imagine we've got these 2. So consider this, C1 V1 plus C2 V2 equals 0. Consider them dependent. Let's imagine that they're dependent. So this equals 0. There's some way of combining them for some C1 and C2 not equal to 0. There's some way of combining them to make them 0, right? That's the dependent idea. And so we're going to have this. And we have lambda 1 not equal to lambda 2. This is the idea. They're distinct. So this is the distinct part here. Whew. Okay. Okay. Yeah. I guess I didn't do that. All right. Okay. Good. Okay, so we're going to do a little argument here. Let me see if I can squeeze it over here. So we're just going to take this statement and play with it in a couple of ways. So, so 1, just multiply it all by A, V1 plus C2 V2. So that's C1 times A V1. Again, the monks are doing these things, all right? So it's A times V1. That is C1 lambda 1 times V1. And then C2 lambda 2 times V2. Right, so this is 1. Let me write what I'm doing here. This is pre-multiplied by A. Yep. Or the second approach, which is just multiply by lambda 2, which is much simpler. So we're just going to take this and multiply this by lambda 2. So now we get C1 lambda 2 times V1 plus C2 lambda 2 times V2. In both these cases, all of these things still equal 0, equals 0. So I've got this equation, and this equation. So the A came in and created a lambda 1 here and a lambda 2 here. I know this is a bit small. Lambda 1 here and a bit of a detail thing. Lambda 1 here and a lambda 2 here. But just multiplying by lambda 2 puts a lambda 2 here and a lambda 2 here. So we can subtract 1 minus 2. I'm going to subtract these two off. These ones cancel, right? They just cancel each other. And we'll get C1, and then lambda 1 minus lambda 2, V2, V1 I should say, V1 equals 0. And this is only true, lambda 1 is not equal to lambda 2 by assumption, so it implies C1 equals 0. Okay. So you can do the same and show, can similarly show C2 equals 0, and then this is a contradiction. All right, it was a proof by contradiction. We said there is some way to combine these two vectors to get 0. Here's our statement about linear dependence, and then we multiplied it by two different things. We multiplied it by A, which resulted in this equation with a lambda 1 here and a lambda 2 here, and we multiplied it just by lambda 2. So they look pretty close to each other. The difference is here. I know, that's just tediously horrible. I need a better proof for that. Okay. Linear independence. Okay, all right. The idea is then, from here you can kind of move up to n eigenvectors. That's all we're going to do right there. But just remember this important result, okay? So that if the eigenvalues are distinct, then the eigenvectors will form a linearly independent set. Okay. All right. Okay. So then can build up from there to n e vectors in this way. Okay, that's enough for that one. Fine. Okay, good. So one last one. So sometimes products of matrices, things are good. Sometimes they're not great. This is just something to know about. I'm just going to say it. E vectors and E values of A plus B and AB are not simply related to those of the separate matrices. Right? So there's no special thing there. Right? Sometimes these things are related to those of A and B. Right? So you can't find the eigenvectors for B and then know anything about AB. All right. Okay. So I'll just, so this is just a note. See a piece online. It's referenced in one of the assignments. Piece online about algebraic and geometric multiplicities. And it's connected to the question about it. So that's an important thing to know about. Okay. All right. Okay, so let's get on to this. Okay, good. All right, so it's just a grab bag of results for eigenvectors and eigenvalues. Now we're going to try and get this thing to work. All right, this kind of spectacular machinery here. There's a lot of beauty in this. Okay. It's called diagonalization. And in a way, you're just changing the frame of reference that you have so that you see that it's diagonal, right? You aren't. We sort of think of it as making a matrix diagonal, but That's how it's sort of talked about. But really, it's just unveiling its true nature. Always good. All right. Okay, so here's an observation. I talked about powers of matrices, right, in that one lecture, and said these are great things, you need to know about them, Fibonacci, et cetera, right? But let's look at one particular type of matrix that's easy to raise powers of. So diagonal matrices are easy to work with, right? Very easy to work with. So let's imagine we've got this one. So here's our example. A equals 3, 2, 4. That's it. So it's diagonal. It's zeros everywhere else. And the great promise is that we can actually find this kind of structure in many, many matrices. So what's A to the n? Let's just do A squared. So quickly, so we've got 3, 0, 0, 0, 2, 0, 0, 0, 4. 3, 0, 0, 0, 2, 2, 0, 0, 0, 4. Okay, so there's going to be 3. It's just only going to hit the 3. The 2 is only going to hit the 2. The 4 is only going to hit the 4. So it's 3 squared, 2 squared, 4 squared. And in general, A to the n is, so you don't have to do any computation. It's easy. 2 to the n, 0, 0, 4 to the n. How's that seem? Okay. So the more we can work with these guys, the easier things will be. All right, so that's our plan. And something times, like this, for example. So A to the n times x, that's great, right? It's much easier, right? It's easy. Right? We don't have to sort of do these horrible calculations over and over again. It's multiplying matrices, right? A whole row and a whole column, a whole row. It's nasty business. But these are easy. We don't even have to think about it. We actually just do, essentially we just do what, our normal raising of powers, our sort of naive way of doing it works. Right? If you came along and you never heard about matrices and someone said, what's this, the power of 7, and you just put powers of 7 everywhere, you'd be right. Right? But if there was a 3 over here and you put that to the power of 7, that's a disaster, right? That's going to get entwined and messy, messy, messy. But the sort of naive power raising works now. So that's easy too. All right, so let's go back to our example. So back to this little character, A equals 1, a half 1. And if we could work in this coordinate system, okay, so here's V1 was 1, 1, and here's V2, which is minus 1, 1. Let's make these dashes, da, 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 da. So the idea is, and this is x1, this is x2. This is, and these are at right angles actually. This is A's natural coordinate system. So instead of referring to our normal basis, so if we had a vector here, we want to actually write it as that's its position. Nothing to do with x and y, right? We don't want the x1 and x2. We'd actually want to break it down into how much of v1 it has and how much of v2 it has. So the idea, if we can express vectors in terms of v1 and v2, A's action, A's behavior will be very simple. A's action will be very simple. Right, so somehow if we can kind of rotate these axes, yep. Okay. Right, and turns out we can. So if A has n linearly independent eigenvectors, it's not about eigenvectors, it's about the eigenvectors, then we're all set. We're all set. We can diagonalize A. Okay. I know, it's tremendous, very exciting. Okay. Oh, we can diagonalize A. So let's do that. Let's do that crazy thing. Wow. I will not fall over. Okay. Okay. Some truth. Okay. Good. Good. This one? Nope. Okay, so let's get it to work. All right. Okay. This place is toast, right? All of this. It's going to be knocked down, yeah? Such a nice ball. So sad. Whiteboard using filth. Crazy people. All right. Okay. Okay, we're going to diagonalize A. Yes! Okay, so we know this. We know A times VI equals lambda I VI, right? For I equals 1 to n. Let's do something crazy. Let's put them all in a box. Okay, so we're going to create a new matrix. A new matrix with E vectors as columns. Let's just do it. Yes. Total monk work. All right. So we're going to call it S. So it's fun. Call it S. There will be a Q. Not yet. S equals V1. We're going to stack them up. V1, V2, up to Vn. That's it. Just lay them out, right? Okay? All right. And now we consider this. We're going to think about this. I've got a couple of spaces for this. So consider, this is obviously monks at work. Let's consider this. A times S. Right, I mean, the vectors are here. A likes to multiply these vectors. So let's consider this. A times S. Okay, good. So we're going to have, let me write here, AS, and I'll put everything in. It's A times all of this, V1. They're all in a row, V2, over to Vn. Yes. And then, can I do this? I'll go here. Okay, so the A is going to come in and multiply each column. We have to remember these kind of funny, more elevated ways of multiplying matrices. The next step will be this. So it equals A times V1. That's a vector, right? This is an m by n, and this is an m by 1. So this whole thing is an n by 1. There. A times V2. Just magnificent. A times Vn. So what's the next step? Yes. We have to do that. We're just begging for it, right? So lambda 1 times V1. Lambda 2 times V2. Lambda n times Vn. Right, so we use, this is the first part, this is actually where we use it, that's it. So we use the E vector equation. right? Column by column. So what about the next step? We want to extrude the lambdas. Yeah, so which side does it go on? Want to go on the left, right? Yeah. So it's true. You have to sit here and think about this one. The A came in from the left. And it's true the lambda's just sitting there. It's on the left, but it's a number, so it can shift around. But the next stage actually looks like this. So it's going to be, let's think, we'll stand back. I'll write it down, we'll stand back. V1, V2, Vn, and then we can put the diagonal matrix. Lambda 1, lambda 2, lambda n. This is zeros, zeros, all zeros, zilches. This big, right? That just means lots of zeros. So how is this working? Let's think about it. So this, think about this as an A times X sort of thing, a column picture kind of thing. So this would be just lambda 1 times the first one, crush everything else. The next one says I just want that vector times lambda 2. The last one says I just want lambda n times this vector. Right? Each one by itself, if you think is like a column picture thing, right? So this one says, I just want lambda 2 times that one, and 0 of the rest. That's that one, and then put that into the second column. So this is what we started with. It's A times S. It's the S. We got our S back, yes.
So get from that one to that one, you just almost like, not divide, you factor it. You take that one right there on the bottom and then
This one?
the lambdas to get that second matrix.
Yeah, I mean, that was definitely, there's sort of a path, like we know where we're going kind of thing. We're trying to make this matrix come back. And if you stare at it for long enough, you realize that the way to do that, right? So that each column here is being, so this whole column is being multiplied by lambda 1. This whole column is being multiplied by lambda 2. And so a way to then turn into a product of matrices is that this will do it, because this column here, it's all zeros except lambda 1 there.
So you factored it out.
Yeah. Oh yeah, sorry. Yeah. Right. No equal signs were harmed in this operation. That's true. Okay, so this is S times capital lambda, which is a fun thing to draw. A is stronger. A does hold up better. It's got that cross bridge, right? But lambda's pretty good. Okay, so this is pretty cool. I think it's pretty cool. So we can write this in two ways. So we have, okay, so we have this A times S, again, which has all the eigenvectors in it, is S times, right? This is very simple. Very simple, right? Simple, very simple. So so we're going to connect this to transformation of basis and all sorts of stuff. So I've got that one. We can rewrite this if we can find the inverse for S. So now we can say A. See if you can write down the next step. What's A in terms of these? Well, it's on the board. Okay, all right. I try. Okay, so post-multiply by the inverse of S, and that will clean this one off and put one over here. There's that. Or, if you like, this is less of what we'll use, but this is true too. We could say pre-multiply by S to the minus 1, we get this. A, S. So this is known, this kind of thing where you have these two matrices here, there's some transformation like this. This is called a similarity transformation. And it's the technical term. We say that A and lambda this thing are similar, are said to be similar matrices. So it's a bit of a soft use of that word, similar. But, okay, so let's see if I can do one example for you. So what's going on? Eek. I'll just state a few things and then we'll try to work through an example. So A times X. So now we can think of it like this. A times X is, there's an S, there's this character, and then S to the minus 1 times X. And what we're going to see is that, right. This guy changes X into, changes the representation of X, representation of X into A's vector base, eigenvector bases. It doesn't change X. It just says this is X with respect to a different coordinate system. It doesn't change X, right? This does the actual work. So lambda does the actual work of A. And this S undoes it and changes back to the normal basis. Right, because all along we've said, all right, there's this dark Descartes thing, whatever, right? I had JK. We've just set that. Everything's with respect to that. But this is where this is actually just changing your point of view. This is doing the work. Okay, and let me say one more thing before we try to work on an example. So what about A to the N? So that's going to be this S lambda. So there's going to be more about this. So, right? So there's going to be more soon, okay? About that. What about this? We're going to raise this to the power of N. Yes?
How come the S and the S inverse don't just cancel out?
You mean?
Like, how come it's not just I and then uppercase?
So that's, how come they don't come in here and get each other? Yeah, so they've got a lambda in the middle. So, and this is, if this was an identity matrix, then they'd hit each other. But there's a diagonal matrix with numbers along the diagonal, which are not 1, that's mess with things, right? So you're not, then they can't touch each other. Yeah. You have to, this has to multiply this one, which has to multiply this one. But over here, this is different. This is the thing you're looking at, I think. So what about this? Let's S to the minus 1. That's the first one. And then S lambda, S to the minus 1. And then S lambda, S to the minus 1. There are n of these. What's happening? Let's make it K. I'll make it, oh, it's all right. Nope, it's going to be K. K. What happens? A good thing happens. Yeah, because these are all going to hit each other, right? Yep, good. So there'll be an identity in here. All of these things become identities. And so we end up with just S, and it's just the lambdas to the N, S to the minus 1. Okay, so let's quickly work on our little example. So, okay, so our example, A equals 1, what did I say, a half? Yeah, a half 1. Well, we had S equal, we'll just stack them together. 1, 1, minus 1, 1. And then, so this is V1 and V2. And our lambda matrix is 3 halves and a half. This is the real A. At least when it comes to multiplication. So we've got that. We need the inverse of this thing. What's the inverse of that guy? Determinant is 2. We can use the formula. That's fine here. Right, 1, 1, minus, minus 1. This is a 2. We swap these ones, and we put minus signs here. There is something about the inverse of S and S. What is it? So it's very close to being the transpose. Close to having S equals S to the minus 1 equals S transpose. And it would be true if we normalize these vectors. If we put a 1 over root 2 here, there'd be a 1 over root 2 here. So we're going to come back to it. It's a huge deal. Would true for, because S, it can be any multiple of these things, right? True for 1 over root 2, 1, 1, minus 1, 1. Normalization. Okay, so if we want to raise this, and this will be a good place probably to stop. So if we have 1, a half, 1 to the power of, 73, then that would be equal to, so we'll put our S in here, 1 minus 1, 1, 1. And then we would have simply in here the thing that drives everything, the 3 halves to the power of 73, 0, 0, a half to the power of 73. And then we have our S to the minus S to the minus 1 at the end, which has to have a half there. A half, 1, 1, minus 1, 1. So there's one last step, which would be to multiply these things together. But you can see what's going to happen to this half to the 73. What's happening to that? Right, so that's going to 0. And this is driving the bus here, right? So one last thing is that the largest eigenvalue dominates systems, where you have multiplicative systems. It dominates systems. It's the thing that wins out, by magnitude, that is. So 3 halves is the big winner here, right? And anything that's less than a half, less than 1, just gets trashed. All right, we'll do some more with this example. Oh my God. And yeah, good. Pitfall is due on next Tuesday. Exam from two weeks from today. And a birthday. We'll celebrate a birthday.